Lab 4, Modeling Circuits in Software. For this lab, I predicted the behavior of series circuits and resistor capacitor circuits. I then used the circuit constructor kit from Colorado FET to observe the actual behaviors of these circuits, and to compare these behaviors to my predictions. For the resistor capacitor circuit, a time constant of 6.08 seconds was observed. This will be explained momentarily. There are a number of important physics principles at play here. The first principle is the Kirchhoff loop rule. This states that the voltage difference across a closed loop in a circuit will always be equal to 0. The second important physics principle is that voltage is equal to the current times the resistance in a resistor. The third important physics principle is that the voltage across a capacitor is equal to the charge of the capacitor over the capacitance, a constant that describes a capacitor's ability to capacitate. The third important physics principle at play here is that the current flowing into or out of the capacitor is equal to negative dq over dt. Combining all of these ideas, by the Kirchhoff loop rule, for a resistor capacitor circuit where the capacitor is discharging, Q over C minus IR equals 0, as those are two voltages that together must be equal to 0 if they themselves form a current loop, and therefore Q over RC plus dQ over dt equals 0. That is simply substituting various terms that we've listed before into the equation we just created. This is a differential equation, and it can be shown that this is equal to the equation natural logarithm of voltage over initial voltage is equal to negative time over RC, where RC is resistance times capacitance. I say this can be shown. I will leave the proof as an exercise for the grader. The first part of the lab was constructing a series circuit with two resistors of the listed resistances, 2 ammeters, and 2 batteries, each with 1.5 volts of potential. I predicted that the ammeters would both measure 0.02 amps of current, and that is exactly what I measured. The top ammeter was then replaced with a voltmeter. This resulted in a current of 0 amps and a voltage of 3 volts. This is because the circuit was incomplete and there was no current flowing through it, resulting in a measurement of 0 current. However, the voltage potential was still 3 volts, because there was still a potential difference across the circuit, even if current was not flowing because the circuit was incomplete. Current does not flow through the voltmeter, as the voltmeter has effectively infinite resistance and therefore 0 current flowing through it. The top ammeter was then replaced with wire to close the loop of the circuit. The voltage potential difference across the circuit at its various points was then measured using a software voltmeter. The voltmeter was always used such that the red lead, or the positive lead of voltmeter, was in contact with the circuit upstream of where the black lead, or the negative lead of the voltmeter, was in contact. By upstream, I mean backwards relative to the direction of the arrows as indicated on the diagram. I got the readings listed in the diagram above, and I measured a current using the remaining ammeter of 0.02 amp. As discussed earlier, the Kirchhoff loop rule tells us that the sum of all of these voltage differences should be equal to 0, and sure enough, it is. Using the data earlier, I was able to construct this graph of potential relative to the negative terminal of the batteries, relative to the position in the circuit. When we attach the voltmeter, we do alter the circuit. However, as the voltmeter offers effectively infinite resistance, it has no impact on the actual current measured anywhere in the circuit. When we connect the voltmeter across the 100 ohm resistor, the ammeter reading is still 0.02 amps. However, if we replace the voltmeter with an ammeter in parallel to the 100 ohm resistor, the current through the other ammeter increases, as the total resistance of the circuit is decreased because the ammeter offers effectively 0 resistance, thereby allowing the current to bypass the 100 ohm resistor. From the earlier data, we are able to calculate that our 47 ohm resistor has an actual resistance of 47.95 ohms, and that our 100 ohm resistor has an actual resistance of 102.05 ohms. The wire and the ammeter both have 0 resistance. These differences are probably due to rounding in the software, as there are no measurement errors given that all of this is stimulated anyway. Next, I constructed this resistor capacitor circuit. The light produced by the 10 ohm bulb started very high, but very quickly decreased as the capacitor charged, and therefore current flow through the circuit decreased. When the bulb was connected just to the capacitor, it glowed very brightly, but then very quickly petered off. This was due to the capacitor discharging. This would start off very high, and then very quickly decrease as the charge left the capacitor. When the capacitor was charging at the very beginning, current started quite high, just as the light of the light bulb, and then decreased quite quickly, just as the light in the light bulb. Similarly, when discharging, current started very high, but decreased rather quickly, just as the light in the light bulb did. Using the stopwatch provided, I was able to measure that the 10 ohm bulb allowed the capacitor to charge in 11 seconds. When this bulb was replaced with a 20 ohm bulb, the capacitor took 18.42 seconds to charge. Finally, this circuit was constructed using a 200 millifarad capacitor and a 30 ohm light bulb. The capacitor was charged using a 9 volt battery. Then, the capacitor was discharged into this circuit, and the voltage difference across the capacitor was then measured regularly over 20 seconds. This data was then plotted in order to calculate the time constant of this circuit. Using the equation whose derivation I left to you, we can plot the natural logarithm of the measured voltage difference divided by the initial voltage difference relative to time. Then, we can take the slope of this graph, and using that equation, we can say that that slope is equal to negative 1 over RC. It is then trivial to solve for RC, the time constant of the circuit. In this case, the time constant of this circuit is 6.08 seconds, very close to the predicted value of RC, which is 6 seconds. Here are some final closing questions. If we did this lab in real life and used actual ammeters instead of simulated ammeters, we would have measured slight resistances in the ammeters, as a real ammeter cannot have zero resistance, just as real wires could not have zero resistance. This would have affected the circuits because we would have measured slightly lower current flowing through them, as they would have had a small third, or in some cases second resistor. Our model predicts that with no resistor in the circuit, the capacitor should charge instantly from the battery. In practice, of course, this will not occur, as real batteries have some small quantity of internal resistance.